right. It's great to be here. So my name is Jiang Chen. Today I'm going to give a talk about how we power the billion-scale vector search at Milvus with Apache Pulsar. So something about myself. Currently, I'm leading the ecosystem integrations and developer relations at Zillis. And Zillis is the company behind Milvus. We actually created this open source project back in 2019 and then donated the project to Linux Foundation. So Milvus is the first open source vector database in the world. At that time, there wasn't really a term called vector database. Something about myself, before I joined Zillis, I was doing search indexing at Google. So at that time, we were dealing with hundreds of billions of web data at a really gigantic scale. And I kind of got into this domain, like search indexing, search infra, a few years ago. And at Google, the way we do this is by having a dedicated piece of infrastructure for serving the vector embeddings. And we didn't even really have a term for this piece of infrastructure. So that the first time I learned about Milvus, I was really amazed that something open source that was created outside of the large web giants like Google or Facebook, and it's kind of democratizing this technology to the open source users. So that's how I got into this space. And then I quit my job at Google and joined Zillis to work on the open source Milvus project. So today my talk will be primarily focusing on how we build a more scalable, more performant vector search. How do we power the? Is that showing this? Okay. How do we power the endless use cases in the GenAI space, like RAG, image search, multimodality search, with the open source technology? And also, in addition to the use cases, I will also touch a bit on how we build this infrastructure internally by using other cloud technology or like open source projects like Apache Pulsar. So before I dive in, I want to run a quick poll. How many people have heard about vector search or vector database? Okay, we have a fair amount of people familiar with that. How many people know about RAG or retrieval augmented generation? Awesome. Yeah, so I think we can maybe dive a bit deeper and make this more fun. So I'll quickly scan through this, but basically why do we even need a vector search? And right now, people who are using, say, chatbot or like AI, so-called AI-powered search, will be familiar and kind of take it for granted. Like I just type some query, somehow it magically just retrieves some information from the internet or my internal kind of private knowledge base, and then return a very grounded and human-friendly answer. Which is generated by a large language model. So this is an example from Perplexity. And things like Google AI Preview, they all use the same piece of technology, which is they use the traditional search infrastructure to do data cleaning, to parse and do semantic understanding of the content. And then with all that information they collected from the data cleaning process, they convert those document chunks or images into vector representation to represent the semantic behind those content. And then at serving time, they convert the user query with the same embedding model to vectors, and then do vector similarity search to find the things close to the target vector. And those, the machine learning model guarantees a great property that if the vectors of those documents are closer, then the semantic of them are closer. Well, why? Because that's how we design and train the models. Like that's an objective, and by having tons of training data, we can maintain this property and create those embedding models. So with that, now we have another data problem, which is we have a lot of vectors. We may have millions, or in this case, if that's worldwide, we probably have billions or hundreds of billions of vectors. Then how do we efficiently store them? How do we efficiently retrieve them at serving time so that you can get all of the results within maybe like 20 milliseconds, and then spend another 500 milliseconds on large language model generation, so that you have this very good end-to-end user experience, right? So another angle to look at this is for the this search is not a new problem. It has been there for 2 decades. Like Elasticsearch or like Google in the past has been putting a lot of engineering resource on this problem. And traditionally, this was done by a thing called a full text search or lexical search, which is pretty much just mechanically matching the keyword of the query and the documents, so that you can, if you have, say, rising dough, and then you search for dough, and then there's a high likelihood that you can retrieve that. But what about if you are searching for proofing bread, which doesn't really have any overlapping in terms of keyword? But in fact, it just means exactly the same thing, right? So that's where vector can come into play. By training these machine learning models to generate vector embedding, it doesn't really look into the individual words or tokens. It just kind of it kind of takes the holistic view of the piece of content, and then generate a representative list of numbers to kind of extract the essence of the semantic behind those content, and even more like interestingly, it can work with images, and also other more kind of a complex content type. Like on the very right, we have the diagrams, we have tables, and sometimes we even have tables that's like scan tables, which are not even in textual format. They are just purely image and pixels. So that with all kinds of advancements in the deep learning, we have vision language models, we have multi-embedding models, which we'll cover in a bit, so that we can tackle not only the text search problem, but also image search, video search, and audio search, right? You can even in the future probably search a piece of text with a table, which is an image itself, but it has some kind of a textual information which are related to the query text. So this just unlocks a huge amount of innovative use cases. And adding on top of this, there are predicted 90% of the new data being generated everywhere, like from the World Wide, from the enterprises, they are unstructured data. Like unstructured data mean anything that's not a SQL table or relational table. Like for example, documents, files, PDF files, images, audios, right? So with the vector embedding, or this paradigm of using vector embedding to represent the semantic of unstructured data, and then leverage those information by doing vector search. So with this paradigm, we can make better use of the enormous amount of unstructured data that are exponentially growing. And a bit deeper dive into this paradigm, like as I mentioned, to do this vector search, you need to have a deep learning model, which is usually which is a deep neural network. It could be in BERT architecture, it could be in large language model architecture, and those are specially trained for generating vectors that can represent the semantic of the any kind of unstructured data from your knowledge base. And with this, you have a bunch of vectors, and these vectors, I mean, we all know that vector is just a list of numbers, and then you can represent as a point in the high dimensional space, and we can, visualize this as the as the very left, and then for the search, you somehow plot your target vector in the high dimensional space, and you find the vectors that are the vectors of the documents that are closest to the target vector, and then return top K. So that's kind of in a nutshell how all of the vector databases are working. And with the great property of the embedding model, you have things with similar semantic close to each other, so that if you can do this, we call it nearest neighbor search. If you can do this nearest neighbor search really well, then you can achieve the business objective, which is to find the documents that has closest semantic to my target query. So with this problem, we think there might be a dedicated piece of data infrastructure designed for this new workload. So in the past, say at Google, the way we do this is we just write some logic and then build our own infrastructure, which is not designed for any general purpose vector search. It may be specialized in, say, serving the web data. In that case, the web search has a particular pattern, which is periodically updated. So it has a batch layer or like a stale layer, and then it has a fresh layer. So for the stale layer, it uses something similar to vector database. It implements the vector similarity search algorithm, but the infrastructure is not really designed for both streaming case and not designed for both the streaming data and the batch data. So that the way it does this, it has two pieces of systems. One system is just used for handling, say, 500 billion web pages, and that's updated, say, like every week or even more, like less frequently than that. And then it has a fresh tier so that you always have, say, CNN News updates like every minute or even more frequent than that. You want to catch that to show that in the search results. So you need a different piece of infrastructure just to handle the streaming part, right? So we kind of think this from a different angle. We think maybe for external users, they probably don't need that sophisticated infrastructure, or they don't really have enough people to manage that sophisticated kind of system of very complex components. What if we just build a general purpose vector database that can be used by anyone doing semantic search, whether you are searching for image, whether you are searching for web pages? I mean, there will be some common requirements for them, right? And not everybody is handling with 500 billion data sets. Like most people, they're just handling with, say, 10 million or like 1 billion. So that with this in mind, we designed the project, open source vector database project called Milvus. And it has been surprisingly successful. So very luckily, we are loved by the open source community, and now we have 30,000 stars on GitHub, and we have over 400 contributors and over 66 million downloads. And some of the reasons I think which made it kind of popular is it's relatively easy to get started with. So that we have the main Milvus offering. In addition to that, we also have this pip installable thing called Milvus Lite, which you just need to do pip install PyMilvus, like Python Milvus. And then you can use this vector database in your local, say, laptop or notebook. And then if you want to scale further, say if you have 10 million vectors, like you want to serve a website and you are full stack full stack web developer, then you can use the Milvus standalone, which is a version of Milvus that can be run on Docker. And then if your application is very successful and you need a lot of scalability and high performance, say if you want to serve 10 billion data at 10,000 query per second, if you have that scale, we also have the Milvus distributed version, which runs on Kubernetes, which has disaggregation of storage and compute so that you can scale the write traffic in isolation of the read traffic, or if you have a different traffic pattern, you can configure the amount of nodes for the write and read, and then have this flexibility of serving very, very high scale of traffic. And then all of these instances, they share the same API, so that it means on the client side, you just need to develop the client side code once, right? Say you develop the vector search and vector ingestion logic in your application server. You just have the same piece of code. You can you can reuse this code from a prototyping stage to a lightweight production stage to like really gigantic, running a gigantic cluster in the production. I know, for example, for a mission critical business like of billion values. And in addition to its core capability, we also extend the integration of Milvus to the popular GenAI developer stack, like Llama Index and Longchain and Haystack, all those tools that you use for building your RAG pipeline. And we also have tutorials on how to use, say, OpenAI embedding models, Voyage AI, GenAI, or open source BG embedding models with Milvus. We also work with other kind of ecosystem partners in this RAG development stack, because in addition to developing this piece of logic, this pipeline, you also need evaluation, say RAGAS and Arise and Phoenix. We work with them so that it's easier to retrieve data from the Milvus vector database and use that to evaluate how well your RAG pipeline is performing in terms of context relevance and context precision. And lastly, in addition to the core vector search capability, it also has like advanced features such as hybrid search. For example, this semantic search that we talked about, that's great. That gives you the right amount of fuzziness so that even if the keyword doesn't match, you can still retrieve the data. But what if you also want some kind of control over what kind of data you retrieve, or you want to have some predictability, kind of make the retrieved data predictable. And that's where, say, full text search is very useful, right? Because it has a simpler logic and simpler behavior, which is unlike the vector semantic search that usually gives you semantically relevant data, but it's very hard for human to predict what kind of results it will return. So that combining these two will be very helpful to a lot of use cases, as we've seen from our users. So that we created this dense and sparse hybrid search, so that for the dense vector, that's what we mentioned before, you use it for catching the semantic. For sparse embedding, it's kind of equivalent to full text search or BM25. So with that, you can just get the amount of control over the returned data. Like you can predict if the keyword matches, then it will very likely to get your result back. So that's on the retrieval quality part. On the other business logic, for example, we support metadata filtering. What if you want the semantic search, but also in addition to some filtering logic? Like I want semantically similar documents that matches some predicates, like the published date is after some timestamp, or is belonging to some particular organization. I don't want to return the organization that doesn't belong to the user who sends the query. And then in addition, we also has integration with the re-ranker models. So say if you have the dense embedding model as the first stage retrieval, that it gives you a reasonably well-ranked list of results based on the vector similarity or vector distance. And then maybe you think that's not good enough. You want to further refine the result. You can use a thing called re-ranker model, which gives you better relevant ordering of the documents. But it also has its limitation, which is it's very expensive because it will need to compare the full text of all of the candidate documents that you send to the re-ranker for it to re-rank. And it's way more expensive than just compare the vector similarity, right? The vector search kind of carries a good thing from traditional search system, which is to do all of the heavy lifting things offline. Like you compute the vector embedding, which is not that cheap, offline. And then you have all of the vectors stored in the system. So on the online serving time, you just query, you just compare the query vector with all of the document vectors, which you have pre-computed offline. So that will be way cheaper than, every time you search a query, you get 10 results, and then you compare this query with each one of the 10 results to get a better re-ranking. But for some cases, you really care about the relevant ordering of the results, then re-ranking is a good tool that you can leverage. And we're very happy that the Milvus project is trusted by a lot of enterprises in addition to developers. Some known names like Salesforce, Airbnb, and eBay. So we work with those customers, and they usually have a larger kind of a larger deployment or larger data scale. So that help us to explore the frontier of vector search and deal with kind of tricky things like how do you handle multi-tenancy as well as high performance, and how do you handle the manageability, like ease of management, in addition to provide the right amount of flexibility to the users. So I will cover a bit more on that trade-off later in the architecture diagram part. But just to summarize on the high level, I mean, vector search, that's a very useful technology that powers a lot of use cases, but it also has a lot of challenges. So some of the known challenges are, first of all, you need to solve the problem of indexing vectors. Right? Vectors, they are just points in the high dimensional space. Unlike traditional data, which you can build an inverted index. For vector, you just simply cannot build an inverted index. It's not like a string or a number. So some of the popular ways of building index include, say, doing partition. Like I partition the whole high-dimensional latent space into a few components, or I cluster the existing data to define the partitioning of the space. And then for each search, I define. I first tell which partition it may belong to, and then I only kind of traverse all of the data points in that space, in that subspace. And there are more advanced algorithms like based on graph, so that you basically draw a map of major cities in the high latent space, and the major cities are those maybe like randomly selected vectors, or you can have some heuristic to better select the vectors. But basically, you have some sample points in this high dimensional latent space, and then you define a graph to kind of note where are they. And for the search, because you have established route between those nodes, so that you can traverse the graph and find the point close to your target vector. It's a kind of greedy and heuristic-based algorithm. And there are also, one of the most popular graph-based indexing algorithm is called HNSW, which creates this graph, but like layered, so that on each layer it may have different level of, like it has different level of density. Some of like the top ones are very coarse, but at the very bottom, you pretty much link all of the nodes. So we support, so Milvus actually supports all of the indexing algorithms, in addition, including the tree-based, partition-based, graph-based, and also disk-based indexing algorithm. And we also, in the past few months, we have supported GPU-based index as well, which gives it a bit more power, leveraging the parallelism of GPU. With that, we also need to solve the scalability problem. Like some of the vector databases, they are good at, say, 1 million, 10 million level, but going after that, there is a lot of scalability problem to tackle. And I'll kind of show a bit more details on that with the architecture diagram. And also supporting multiple data types. So in the next major release of Milvus, we are considering support a feature called data in, data out, which kind of redefines the vector database. Right now, vector database take vector as input, but a lot of users, they think this is just very hard to comprehend for a human being. Like I prefer I just send it a piece of text or the URL to an image, and then somehow it magically has generates the vector for me, and then like do on the search on the query side, it also takes the query text as the input and then just give me all of the text of the candidate documents. So we are experimenting with that design pattern to expand the Milvus API to accept not only vectors but also raw unstructured data. So that will be released in the next version, which is Milvus 3.0. Currently, our version is 2.4, and next month we are going to release 2.5, which has some incremental features, including a better hybrid search feature that I just mentioned. So in addition to tackling the major problems there, we also have some kind of features designed for the production and enterprise use cases. Some of the examples being, for example, dynamic schema, that we support not only predefined columns. So if you have a lot of like new columns being added dynamically, then we support accepting that, and internally it just uses a JSON to store all of the schema that, all of the columns that not predefined in the schema. Hybrid search, which I have just mentioned. On the security side, we have RBAC support, so that if you have multiple tenants using the same cluster and you want to create some kind of isolation or access control to the shared users, you can define like who can access what database or like what collection of the Milvus instance. We also support users with million tenants. Like for the multi-tenant, if you just have, say, less than 10 tenants, then you can create 10 different collections to model different users' data. But say if you are serving some end users and consumer users, and you probably have millions of users, and you want to isolate the users by a virtual field. In your case, you can define a column, and on this column, you can also define like, I want to partition based on this, so that my typical query will only involve one particular username. So in that case, you can store the data of millions of users in the same collection, but also creating this both abstracted level and physical level of isolation. On the abstract level, of course, each row has a different username, so that you can use a feature called metadata filtering to filter, I want the closest vector to this target, but the username needs to match one particular value. And internally, the way we run this query is by looking into the partition map and go to the physically isolated shard, which carries all of the users that has a say hash number equals to say 5. And with this, you don't really need to go through all of the whole data set in the database. You just need to go through say 1/16 or 1/64 data of the whole data set, and that makes the filtering on the username or user ID very efficient. And we also support bulk import. This is a feature that you will find very useful if going into production, because in production, maybe like at the initial phase of establishing the whole collection, you want to bulk import like 100 million data at once. And doing that incrementally, that will be very inefficient, so that we support the bulk import feature, which lets you to do this more efficiently. Okay, so there's a lot of useful features loved by our developers, but how did we achieve this? So everything starts from this fully distributed architecture. So that from very early days, we have noticed that the vector search workload will become really, really high scale. So on the large scale, to run this workload on the large scale, we probably need some flexibility. There are different design philosophies. I know some vector database, they are designed primarily as a single machine architecture, which makes it easier to operate, of course, but also sacrifice the potential of scalability. So that we kind of think this problem from a different angle. We think in the future, the larger scale of vector search use case will get more and more popular because the explosion of the data, because this use case gets more and more popular with RAG and multimodal search. So that we design this fully distributed architecture. Like it's very complex, but I can briefly walk through this. So on a high level, we have data and compute. We have storage and compute disaggregation. So on the architecture diagram, you can see that we have the object storage layer and we have the worker nodes, so that all of the worker nodes, they are only responsible for computing, like building index, serving the queries, or like loading data and offloading data. And then below that, we have the object storage layer, which leverage, say, Minu or like S3 to store all of the source of truth. And on top of that, we also isolate the read and write path with different components. So on the read path, you can see, let me see. Oh, yeah. So on the read path, you can see this red line. So it directly goes to the query node, which is responsible for serving the queries. And then on the write path, it actually goes through a log broker component, which can be implemented by both Kafka or Pulsar. And then all of the data for the write data, it will go through the log broker phase and enter query node and data node. Depends on for the data node, it will process the data, land them into the object storage, and then we also have the coordinator services, which kind of coordinates the behavior of different nodes. For example, if you have a data node collecting enough amount of data, and then it will be landed to object storage, and the index node is notified for that signal, and then it starts to build index for this new segment. And then once the new segment is built, it will be loaded to query node, so that in the future, all of the search on this new segment will be more efficient because now it has index. So this pretty much solves the batch problem. On the write path, we also solve the streaming problem, which is, for data that you have landed on this system for a while, then you have an index, you have a sealed segment. But what if there's growing data? Like for the recently uploaded data, we still want it to show up in the search result. And the way we do this is by having the data streamed to query node, so that the query node is kind of looking at two pieces of data. One piece is all of the growing data that has been just ingested in the past, I don't know, like 30 seconds or a few minutes. On the other hand, it manages the segments with a more established vector index, which stores all of the data before that cut off. So that with this, it's able to serve the majority of the data very efficiently, and in addition to also serve the recently ingested data, so that it guarantees the search freshness. And the log broker components is very critical for us to achieve this, because it simplifies the architecture. We don't need to directly route the data to, say, query node and then have someone, directly processing the ingestion request. Instead, we let it go through the log broker, so that it creates materialization. It creates scalability of handling the write traffic, the ingestion traffic. And particularly, we like Pulsar more in the higher scale use cases. For example, for our commercial offering, I mean, this is open source, but we also have fully managed Milvus on this cloud, where we run thousands of instances of this. So that for that case, it's very important for us to use a log broker that supports multi-tenancy, because we just want to run preferably just one instance of log broker, and that could serve, say, like 10,000 or even more, what's that called, like topics, so that some of the for each instance of Milvus, it may use a few topics. Depends on how many collections you have, like what's your collection configuration. The amount of topics basically controls the amount of throughput that you can have on the write path. So that the more topics the same instance can support, the better, and the less management overhead. In this case, Kafka can support, I think, at most 10,000 topics, but Pulsar can support easily more than that. I think close to 100,000 or something. So that makes a lot of difference in terms of the management overhead. And also, Pulsar, just like us, is worth the storage and compute disaggregation. So that it separates the storage and compute. If we have more throughput on the write, and then we can just scale up the storage side so that we have the same level of handling of the queued data. And if we want, like, if we don't want to maintain a long queue, say we just want to store, say, past 4 hours of updates, but we have a really, really high throughput. In that case, we can just scale up the compute side without, scale up the storage side correspondingly. However, Kafka has a monolithic architecture, which makes it more difficult to do this, or even impossible. But we provided both so that the open source users can have flexibility choosing the one that they are comfortable with. And another thing I want to mention is, remember that we talked about the bulk insert part. Like for the red path that I just introduced, it only talks about incremental insertion. Like if you have incremental traffic, you want the recently ingested data to show up in search results, then having this log broker, that's very important and useful. However, what if you just want to ingest 100 million vectors, like a gigantic amount of data, to the system? In that case, going through this path will be overkill and very inefficient. So that in addition to the in addition to the iterative ingestion path, we also support the batch ingestion path, which is called bulk insert. And the way we do that is by directly connecting the S3 bucket, which contains all of the source data, to the index node and the data node, so that the data node can scan all of the data from the source, which is stored in the S3 bucket, convert the format so that it comply to Milvus internal storage format, and then have the index node to build index on top of that, which, by the way, is very efficient because now you have a holistic view of the data rather than for incremental ingestion. You only know, like, how optimized your index is depends on the sequence of the data ingestion. Right? If you ingest a lot of data which are close to each other, probably your index will be a bit more efficient. But that's really a random process. But on this hand, if we do this in a batch fashion, it gives us more opportunity of optimizing the index because we have a broader vision of the distribution of the vector data. So that's all about the architecture. But all of this architecture is useful and meaningful if we have interesting use case. So lastly, I want to show a few interesting use cases. Some you may have known, some you may find a bit novel. So the first one is retrieval augmented generation. Probably this is not new anymore. Has been a buzzword already. But on the other hand, it's the most widely adopted GenAI use case. So we have seen a lot of users that are not only trying this out, but also working on the optimizations. Say they have millions of users. Some of the user are power user, like they access this data very frequently. Some of the user never really use the service. But all of the user has data, then what do? Like, usually for vector search, to achieve the best performance, you want to store all of the data in memory. However, in this case, do you really want to spend very expensive memory for the users who doesn't really check this app for a year? Like, for that case, we developed this thing called tiered storage, so that you can have the data of the users that are not frequently accessed in the object storage, which is a few orders of magnitude cheaper than memory. And then you can store the frequently accessed data in memory and then do the dynamic swapping of data. Say some user suddenly becomes active on this application. You can load the data from object storage to the memory. So some other challenges being the retrieval quality. Like for this RAG paradigm, it's useful. Like most of the time, it can return result, but I want to increase the most of the time from 50% to say 75%. For that case, I think two very powerful tools. One is evaluation. So if you don't do evaluation, you never really know your quality. So on the open source side, we work with the evaluation frameworks like Ragas and Raz to help our user better do this analysis. On the other hand, we continually improve the so-called hybrid search, which combines the goodness of semantic search and full text search. So in the very next Milvus 2.5 release, we are going to improve the sparse embedding to make it closer to the effect of traditional full text search. So right now there's some nuance. Like for the sparse vector, in order to generate the sparse vector, you need to have a vocabulary first, and the vocabulary is really depend on your document set. Say in the current version, you have to predefine the document set. Which means you cannot really update the documents after you decide to serve the search queries, which is not that practical. Or you can use a vocabulary set from a pre-trained data set, like MS macro, which is a common, I think it's aggregated from some common web pages. But the problem is that what if you have a very special term, like a user's username or a sequence number, which you want to find the exact term in your document corpus. And because you really didn't have this term in the vocabulary, it will be very difficult to find it. It actually breaks down the documents into a few tokens that the vocabulary set recognize. So that will sacrifice the predictability of the full text search part. So in Milvus 2.5, we solve this problem by having a dedicated vocabulary set for each individual node. So remember that we have the distributed architecture so that for each individual node, it will maintain the documents and the vocabulary set for that, so that it can always find the terms shows up in the document. And then there's a multimodality. So in this case, we leverage the model called Magic Lens developed by Google, which takes both image and text as input. So the image describes the rough intention of the search, and then the text is kind of instruction to further enhance that. For example, for this one, I want this construction machine, but I don't want to see the real machine. I want to see the toy of this. And then on the right, you can retrieve the toys instead of the actual machines. Or you can define, like, I want to see this one in the snowy weather. It can actually do that as well. Some less fancy things like recommender system, but which is still widely adopted. So you can use vector embedding to kind of calculate the similarity between a piece of content or say news or some product with the user's preference, so that in this way you can give the user something that they like. Lastly, there's a thing called GraphRag. So in addition to using hybrid search on enhancing the retrieval quality, you can maybe thinking out of the box. What if I have a systematic way of analyzing and mining the information from my document corpus? So instead of searching for chunks, what about based on those chunks, I define my own graph, knowledge graph, like defining the knowledge entities, the relation between them, and then you can encode those information as vector embeddings. Say you can encode the entity names as vector embeddings with text embedding model, or you can concatenate the entities and the relation between them, and then use text embedding model to encode that, so that based on the user query, you can search for related entities or related relations, or related entities plus the adjacent neighbors of that. So that gives you a better chance to grasp the individual concepts in your document corpus, in addition to relying on solely your, however that your documents is written. For example, in their document, it may talk about Kepler, the astronomer. It may talk about, his German, but not really talking about there is a telescope named after these people. So by having this offline analysis of the data, you can establish a more comprehensive relationship between the individual concepts, and this helps increase the retrieval quality as well. Okay, so that's all I want to share. If you want to learn more, feel free to check our GitHub page for the open source Milvus project. And on the right, that's kind of a learning page that we have compiled, which includes all of the implementations of the demos that I showed before, like the GraphRag, multimodality search, and it has a notebook which you can download and then play with it. So thank you, everyone. Yep, that's all.